idea.
Yeah, well, I don't want rabies, but you know.
Yep. Let's see if we can't have a little more fun with this.
All right. I had never seen the pie used for product. That was a new thing for me.
Same thing as Sigma for some.
Makes sense. Makes sense.
But also want to make sure you remember a little bit of math. So let's take our B6 there. How would I calculate the beta 6? What about the P beta 6?
Negative log.
Negative log. And what we're going to get, 1, 2, then we can break this down. How?
Break it down.
What are you going to do with that log and all those multiplications?
You can separate them out, like add them.
Yeah, so like a negative K1 plus log. So we just remember that that's possible. We also want to know, we also want to kind of take a simple reaction and just check to make sure that because you remember we added together multiple chemical reaction steps, and we got this stability constant, which is all of these individual equilibrium constants multiplied together. We want to know, we want to remember, is that true? So let's take a look at carbon monoxide, hydrogen, you get methane, H2O, and I didn't put phases on the others, but we're going to put gas on that because by putting gas on it, where does it end up?
Where does it end up?
If I
It gets
put
canceled out.
well, if I put liquid on it, what equation can it not be a part of?
I don't know.
Can liquids or solids be part of an equilibrium constant?
No.
No.
I couldn't remember the name.
It's a Monday.
True.
And there's always someone who's going to be like, no, they're still part of the equilibrium constant. They just reduced the one because of their activity. I know. But there's always going to be someone. It's like, no, but you have to say that they're still in there. Well, but they're technically not.
They're not. That's like physics, man.
Okay, so once we add this up, we get carbon monoxide, 2H2S, water vapor, CS2 and H2. And we remember that this one has a K1, this one has a K2. Let's do the equilibrium constant for this one, for the total here. This is going to put you way ahead for quantitative analysis.
Great.
Some of the stuff we're doing in here, you're going to be sitting in quantitative analysis board.
Perfect.
Now, the question is, does this equal K1 times K2? Okay, well, you have to do the K value for each one of these. So K1 is going to be CH4. Show over. Cubed. Okay, K2. That was H2 to the fourth. Now, I tried to do a little bit of this in your freshman chemistry class, but there were so many people in there going, I don't wanna, that we didn't get super far through it. Now we're going to multiply these two equilibrium constants. Okay. And I have succeeded in my goal because I've already heard some people opened up the physics assignment, but nope, it closed it.
Yeah, it looked more complicated this week, but
It's not as bad as it looks.
that's the thing. I'm saying if we got it and there's no past session, it's probably something you can do on your own.
Well, and here's the thing, like for example, the question with the matrix determinant
Yeah.
for the cross product, you're going to set it up exactly like you did with the general vectors, except now two of your components for those vectors are 0.
Okay.
It's supposed to be an easy determinant that shows you that that version of the cross product will give you a vector in the proper direction without having to rely on the right hand rule. Okay, so let's take a look here. When we multiply these, let's see what's going to happen. H2 cubed is going to cross out that 4. CH4 is going to cancel out CH4, and we're going to end up with and if we look, that's exactly what our K total is. So yeah, when you add together chemical equations, you do multiply their equilibrium constants all the way through. Oh.
Okay, I like that. That was easy.
Need a little break. Need a little break.
Yeah.
Okay. Man, how much room did I expect to need? Okay. So a pH study of stepwise stability constants at 303 Kelvin was done for this nickel this nickel amine complex, nickel aquaamine complex. So you have the K values as follows, stepping all the way through down to your. So basically, you go from nickel H2O6 to nickel NH36, just one amine at a time.
Yeah. Okay.
Okay. So first off, let's determine the Gibbs energy of step 2. So we can use what we've just been working on to get thermodynamic data, which of course is stuff you would measure in lab. So another way we can connect all of this together. Okay, so now it's a Monday, it's a big question. Do you remember the equation, the Boltzmann equation that connects Gibbs energy to K?
It connects Gibbs energy to K.
It's one of the fundamental thermodynamic equations.
We did.
Which when you take statistical thermo for a PChem, we will derive this equation.
I'll be tired of hearing it at some point.
Yeah, by the time you're done with statistical thermo, you never want to hear Boltzmann's name again.
Is it the one that's like no, B equals M and then there's the two Z's or whatever and then the
Nope.
okay. No, okay. Hold on. I remember this. I can do it. I can find it. Oh, is this the I can't read my own
Well,
handwriting.
the hard thing is, I think I've only put it in here once or twice. and
Yeah.
It was in passing.
And I wrote it down and I can't read what this first word is. That that one? Is it that?
Oh, you're getting closer. You're getting closer. So what you have here is from a negative RTLN of your K value. That's your Boltzmann equation. And this was actually the equation where the whole idea of K came from. Because they were measuring these thermodynamic properties and they were noticing what changed and what didn't when they would put in more reactant versus more product, making the equilibrium shift.
Okay.
And this whole idea of this equilibrium constant came out of it.
Sure. Okay.
Okay, so now what do we have? We have the log of K2. How do I get K2?
10 to the 10 to the log of K2.
Well, in particular, 2.26. Which is going to give me 182. Okay, your R, we're dealing with energy, so this is your (8.314) joules, kelvins, moles, or 8.314 to the negative third. What did I change the units to by doing that?
Kilojoules?
Kilojoules. Okay. And so then my delta G is going negative 8.314 to the negative third. 303 Kelvin. Natural log of 182. We are going to get negative 13.1 kilojoules per mole. And what this helps, and if you did each one of these, what you would notice is that Gibbs energy becoming more and more more positive, showing that the more of these amine ligands we add, the more unstable the molecule becomes. So it's another way to view the stability.
Okay.
Okay, part B. If the first entropy is negative 1.98 joules per Kelvin per mole, confirm that the first enthalpy is negative 16.8 kilojoules per mole. For this one, we're going to have to use one of the laws of thermodynamics. Now we use the Boltzmann equation. If you remember after that, we had this one. So our delta H minus T delta S. Okay, so again, our K1 because we see our log of K1 is 2.79. But first off, I mean, just look at this. K2 versus K1. Do you see how much bigger K1 is than K2?
Yeah.
That means that the equilibrium for that first replacement of a water with an amine ligand lies much further towards the products than even K2 does.
Okay.
So you can start to see how these are a prediction of stability. Okay, so then our delta G. Okay, so what are we gonna want here?
Do we just do the same thing we did on the last one?
Yeah, we do, because we want to find out what the delta H is. And so that's what we're actually solving. Natural log of 616. And that's going to give a negative 16.2 kilojoules per mole. So again, not as stark a difference as you see between the K values, but again, notice how the delta G1 is lower in energy. So it's more exergonic than the delta G2. So you're just gonna, this is the trend you'll find with these coordination complexes. Okay, so then our delta H going to be negative 16.2 plus 303 let's see. Now, you see the negative 1.98 joules per Kelvin per mole?
Yeah.
That's going to be negative 1.98 to the negative third kilojoules. Your delta H will come out to be a negative 16.8 kilojoules per mole. And then C, determine delta G for the equal for this following equilibrium.
So would this be,
Which one is it?
is this K5?
Nope.
This is K4?
Nope.
What?
Use the right hand side of the equation.
K3?
K3.
Oh, because you're counting the amines.
Yeah.
Oops, I was looking at the water.
Nope.
On the left side.
Yeah, you're just counting how many amines were added.
Okay.
Now, if it's K3, that makes it pretty easy. Okay, what do we have? Log K3 is 1.69. Okay. Again, look at that massive drop of the K value. I mean, it's still a big K, so it's still pretty stable, but not nearly as stable as the previous two.
Yeah.
Okay. Delta G3, RT ln of K3. This is going to give us a delta G of 9.8 kilojoules per mole.
Okay.
Okay. Trying to finish up this chapter and then get to the next one. thermodynamic considerations for complex formation. Okay, so hydration entropy is more negative for ions that are highly charged. So is that good or bad?
It's unfavored, right?
Unfavored.
Yeah.
Formation of complexes between highly charged cations and anions with partial or total cancellation of charge has a significantly negative enthalpy.
Enthalpy.
Very favored.
Okay. Right.
So that makes the entropy much more positive. And so in reforming. Yeah, whatever. Your delta G is negative when oxidative cation complexes are formed, so that's highly favorable. Ligands with higher dentate systems form more stable complexes. And so over here, so look at this over here. How many ligands do I have?
You got 3 on each.
3 of them, and they're both bidentate.
That's fine.
Or all 3 of them are. Let's see. Chelate ring. So of course this is a metal ion. So of course these ligands coming in and binding there. That's the chelation process, binding to that metal. Can you see the chelate ring that's formed?
Yeah, the one that's connected to the iron.
Yeah. So
Like
iron.
those 2 oxygens.
Yeah, there you go. So there. There's your chelate ring. Let's see. Here you have the ruthenium attack. See, that's the thing. All of these are abbreviations. Acetyl acid. I still haven't gotten this one.
Acetylacetonate.
Acetonate. Yeah, there you go.
Maybe.
That'd work. And it's not acetonate. That's wrong.
Acetonate. Yeah. Acetylacetonate. You could pronounce it like that, and people would know what you're saying. It'd just be weird.
So with chelating, you get a stabilization with this one, because then bonds are broken. You end up getting delocalized pi electrons. So here's your EN ligand. You'll see this quite a bit in the book, and that's your ethane diamine, and you'll see that at the bottom. The chelating ligands of the 1,2 ethene diamine form complexes with puckered ring structures. Why do you think they twist and pucker like that? What are they trying to avoid?
Are they trying to avoid each other?
Each other. So
Yeah.
what kind of hindrance is that?
Steric
hindrance. They're trying to alleviate steric hindrance.
Work.
Let's see. Experiment shows that small metal ions favor ligands that form 6-membered rings, where large ions prefer ligands that form 5-membered rings. So that's going to, so the smaller, let's say they both have a positive 2, but one's smaller than the other. The smaller one is going to favor more interactions. We've already talked about this. What's the driving factor there?
Like the reduced radius, it's got.
Yep, you're on the right track.
More electron density.
Charge density.
Charge density.
Yeah,
okay.
the charge density is going to be a driver there.
Charge density.
Okay, the chelate effect. Significantly higher stability of coordination complexes with polydentate ligands compared to similar complexes with monodentate ligands. So if you get these polydentate chelation ligands, you get much more stable compounds. You see there's your EN showing up again, and that is your ethane diamine. Yeah, you're going to see a lot of these abbreviations in the book. Just kind of look them up because they're pretty standard abbreviations.
Okay.
Yeah, your ethane diamine. Well, before it's chelated, or before it forms a ligand, it looks like.
Yeah.
That's your ethane diamine. I should ask you if that one is cis or trans.
That one is 6.
That one's cis.
But I mean, they're just single bonds, right? Does it matter?
It can based on,
Is that like a nitrogen thing?
it's more, again, it's going to depend on energies. What is the energy of the cis versus the energy of the trans? And then they have different chemical effects.
Okay.
It just depends on which one's more preferred by the system. So here, you notice that as we go, so we start replacing amine groups, which is a monodentate ligand, with these ethane diamine ligands. So that's a bidentate ligand. And so when we do it once, or let's see, let's see. So yeah, when we do it once, we have to remove two of those amine groups to get the space for the bidentate interaction, and we get a delta G of a negative 13.7. But when we put in three of the ethane diamine ligands, it drops to a delta G of a negative 53. So you can see that these polydentate ligands are causing quite a bit of stability.
Mm-hmm.
And up here's a fun one.
Ooh.
You've probably heard of this one before, EDTA.
I think we've mentioned it in OChem.
So this is an anticoagulant. Let's see. Mm-hmm. Ethylene di, yeah. Don't you love the names?
I do.
So first off, you see that this is a hexadentate ligand, single ligand. You can see the ligand at the bottom before it actually coordinates to the metal.
That's pretty cool. That's pretty cool. Huh.
And then the way this is, so the metal in the middle, if this is an anticoagulant, what do you think that metal in the middle is with your blood?
Probably iron.
Nope.
No. What is that metal?
What is the metal that's more active in blood coagulation?
I don't know. Sodium or something?
Calcium.
Calcium?
Mhm.
I didn't know that.
Yep.
What is, okay.
So that would be, it's finding calcium ions and grabbing them, and before your blood can start to coagulate. Now, that's where you start to lose me. I don't exactly know what you would use an anticoagulant for, but now, here's a question. How many chelate rings can you find?
1, 2, 3, 4, 5.
5.
Okay.
Mm-hmm.
Right, because that other one's open.
Mm-hmm.
Word. I guess, yeah, they're all 5. Mm-hmm.
Okay. Enthalpy contribution to the chelate effect. Let's see, reduction in electrostatic repulsion between delta negative donor atoms. So again, you get rid of those amines. You're getting rid of a lot of electron repulsion by having a polydentate ligand. Such, I think it's supposed to be such as.
Yeah, probably.
Let's see, we get inductive effects of so you see the ligands with your like CH2 bridges. Bidentate polydentate ligands will increase donor strength of the ligand with respect to a corresponding monodentate ligand. So what do we mean by donor effect?
The donor effect?
Mm-hmm. What's the ligand donating to the metal?
Electrons.
Electrons.
Yeah.
You're getting stronger electron donation because here, what happens is the CC sigma bond becomes much more polar when it's in a polydentate ligand system, makes it a better Lewis base.
Mm-hmm. Oh, okay. Okay.
Mm-hmm. And then some factors affecting stabilities of complexes, containing only monodentate ligands, ionic size and charge. For ions of smaller size, stability of the complex with a specified ligand increases substantially as the ionic charge increases, and stability will decrease with increasing cation size. So again, this is driven by charge density of the cation. And then some terminology at the end of the chapter that I really wanted to cover, hard and soft metal centers and ligands. So we come about with like hard acids and soft acids. So hard and soft comes from the polarizability of the metal ion centers. So hard acids are typically either small cations with relatively high charge density or highly charged because of either their size or their high charge. They're not very polarizable. That's the big difference there. They have high oxidation states, small atomic ionic radii. So here's some examples of metal centers, and then the ligands that will correspond to those hard metal centers.
Okay.
So the soft acids, so basically just the opposite. Large cations, low charge density, very polarizable. See low electronegativity, and you get some metal centers down here. And then highly polarizable ligands.
Okay.
The book put it like this: the HSAB, it's hard soft acid base principle. Helps in the prediction of complex formation. Hard soft metal ligand matching gives higher stabilization, it's preferred. So here we have a reaction. If your metal cation is a hard acid, then it will want to associate with water, as that's a hard ligand. Especially so, like if your L is a soft ligand, you're going to keep your aquated cation instead of forming the ML6 complex.
Okay.
However, if M is soft and L is soft and water's hard, you're immediately going to get the formation of that ML6. So you can start to you can start to have an idea of what you need to put together to cause a certain complex to form.
Okay. And it's all just like relative to each other.
Mhm.
Okay.
Remember, but you're looking for, again, we kind of go back to that rule, like dissolves like.
Yeah.
It's kind of similar to that. Hard metals want hard ligands, soft metals want soft ligands. And that actually ends this chapter.
Whoa.
Kind of a long one, but there was important stuff in it.
Yeah. I like that chapter. That was a good one.
Okay, now let's see how much I have of this chapter. Coordination complexes.
Yay. I'm excited for this one.
Okay, so I told you I would get you a little more information on naming.
Okay.
And I'm still going to make you a short assignment. I've had everything in the world to do this weekend.
No, that's okay. I'm also behind on the assignments, which I'll get them in.
Oh yeah, I know you will. So I found a textbook that goes way more into depth with the naming. So you're going to have 9 specific rules for naming.
9 specific rules.
Cation comes first, followed by anion. So remember I was telling you about the bracket notation?
Mhm.
Inner coordination sphere is enclosed by square brackets.
Okay, yeah.
So in the brackets, the metal comes first, but in the name, the ligands come first. Ligands of each kind are indicated by prefix, di, tri, tetra, penta, etc. If the ligand name already uses one of those, or is structurally complex, or the ligand is polydentate, use the prefixes bis, tris, tetrakis, pentakis, hexakis, so on and so forth.
Okay.
Ligands are generally written in alphabetical order according to the ligand name, not according to the prefix, according to the ligand name.
Right. Like in okay.
Yep. Anionic ligands are given O suffix at the end. Coordinated water is called aqua. Coordinated ammonia is called amine.
Okay, okay.
Two systems for designating charge or oxidation number. We've been using the stock system, where the oxidation number of the metal is a Roman numeral, parentheses after the metal name. However, there's also the Ewing-Bassett system, which can be a little more straightforward. Charge on the coordination sphere is put in parentheses after the name of the metal. So, remember we had the brackets, you have like a 2+ at the top?
Yeah.
Well, you could put like cobalt, parentheses 2+. So you could do it that way too. The suffix ate added to the name if the charge is negative. So here you see one, your PT NH34 with a 2+, you see the two naming schemes.
Okay, yeah.
Tetraamine platinum 2 or tetraamine platinum 2+.
Word.
And about the structurally complex, that takes some practice to know what's going to be. So like you're not going to get multiple of these, it just wouldn't happen, but like your porphyrin ring of your hemoglobin, that's complex.
Yeah.
Ammonia is not. So you start to get an idea of what is. That one just takes practice. You already know this, but it's in there, so I'll make sure I include it. Your prefixes that designate adjacent or opposite are cis and trans. And those are based off geometric locations of your ligands. So here, PTCl2 NH32. So you can have cis. Now you notice it's diamine, so amine is A, that's alphabetically first. Chloro, because chlorides are negative, platinum 2. Or you can have trans diamine dichloroplatinum 2.
Okay. Okay, yeah. And it's telling whether they're next to each other, the amines are next to each other, and they're like opposite, like staggered with the chlorines. Okay. Okay.
Now, how would you break this apart and tell me how you knew that the platinum was had a positive 2 charge?
Platinum is one of those common charge ions. Wait, no, it's not.
The amines have nothing to do with the.
It's because the chlorine has 2 negatives. And
you have two chlorides, and this came out to be a neutral compound. So the platinum has to be a +2 because the amines are not going to neutralize.
Sure. Okay. Right.
So kind of like you did in freshman chemistry, just several steps further down the road.
Yeah.
Here you go. Bridging ligands between two metal ions have the prefix mu.
Oh.
So there, it's the one on the left, tetraamine mu dihydroxyl cobalt 6.
So if I'm doing like a crystal structure, anything that connects to other metals. Okay.
Yep. Those bridging ligands are going to have that mu prefix.
Okay.
And there you see that that NH2 is a bridging ligand. And notice how the name changed, mu amido. So it kind of keeps stuff like that in mind too. We're not going to go that far into it. You would do more of that closer to your doctorate, using things that big.
Looks complicated.
It is, but like I told you, I'd find you better rules for naming.
Yeah.
I wanted to show you this because just the name bridging ligand, it's fairly straightforward. But if you've never actually seen what's meant by bridging, I like to show a picture. And so you get how on the left there, your hydroxyls are bridging the two cobalts.
Would you consider those chelate rings as well, like the ones formed?
No, because that there is a single ligand. Well, hang on.
So it's not just because.
Well, no, they actually probably would be. Let me take a look. Okay, so, but then the question is, where are your chelate rings? You have 3 of them. Well, kind of. Yeah, you have three.
On the middle one, there's three.
Yeah, so if you see here, so those would be chelation rings right there. And when your whole complex is negatively charged, the names for metals, the metals in there are derived from the sources of their symbols. Iron is ferrate, lead is plumbate, tin is stannate, gold is aurate, so on and so forth. That you'd have to find a list of those. Those are your Latin names.
Yeah, that's cool.
Bonding in D-block metal complexes. This is why I told you after this chapter, you'll be able to read all the other chapters on metals and go, oh, I get it. So, new terminology. D4, D5, D6, metals, so on and so forth.
Okay.
Your D1, D2. So what do you think we mean by that?
It's gonna be the group.
Yeah, so you look at where the metal is in the transition metals and you count over.
Okay.
So like your scandium 2 plus would be a D1.
Okay.
And
It's the first in that transition metal row.
and it's in particular, it's the number of electrons in the d orbitals that are available to form complexes.
Okay. So it's a little more complicated.
It is, but because you kind of want to think like take your chromium 2. Now chromium, it's going to have it's 3d4, but it has the 4s2 electrons on there. I guess technically you can still call it a D4, but you have a problem with those 4s electrons before you start making coordination complexes. You need to strip those off to make those 4 3D electrons, the highest electrons on the atom, and make them available for the formation of a complex. That's your true D4 complex right there. So your iron 3 is a D5 complex, so on and so forth. So you'll see D4s, D5. These are the things you'll see in articles. And this is what they're talking about. And you can use this trend all the way across the transition metals. Now, we're still going to be using terminology involving hybridization, but we're getting to a point now where the whole hybridization scheme starts to break down. It's like in your coordination complexes, you'll still read articles and hear people talk about an empty hybrid orbital is available to receive the coordination bond from a ligand, so on and so forth. More accurately, though, we're going to use like simplified mathematical constructs with bonding vectors. So it's like these are coming in, like you're just going to have vectors of approach for ligands and whatnot to kind of look at what's going to happen, because we're now very quickly getting into what's called crystal field theory. The textbook makes note of the fact that your dz squared there is formed because you see our dx squared minus y squared. You notice how we're missing a dz squared minus y squared and a dx squared minus z squared. Well, that's because those two come together to form the dz squared.
Oh. Okay.
So you'll just see that little thing, that little aside in the textbook. We don't really need those two, just know those two combine to form the dz squared. Because technically you could also have d orbitals that lie along the x and z axes and that lie along the y and z axes. Let's see. I'm going to do this. Okay, so I want to kind of give you an introduction into what we're talking about by vectors. I just want to show you one. Give you an idea of these coordination vectors. So everything is now going to be x, y, z. Okay. And okay, so what we're going to say, this is always kind of hard to draw, but we do the best we can. Let's start there. And I have this around. So your DZ squared orbital. Now let's say, because what's going to happen in your crystal fields is you're looking at, and you can kind of change that back and forth, crystal field, ligand field. So now let's say we're going to represent ligands as point charges. And they're going to have bonding vectors coming in. And in this case, you see that we're talking about an octahedral complex. Now, DC squared. So what you're going to notice happens is these d orbitals are either going. You know how they start degenerate.
Sure, yeah.
All 5 orbitals are the same energy. Well, they're going to start to split their energies based off the attack of the ligands.
Mhm.
So, what you're going to want to start to think of is when you get ligands that attack an orbital head on, that orbital's energy is going to go way up. Orbitals that deal with ligands that attack in empty nodal spaces are going to actually stabilize and drop in energy. And you're going to start to see that each individual geometry has its own orbital splitting, which is going to then dictate where electrons go. And that's why we get metal complexes that are, we'll talk about, that are both high spin and low spin.
Okay.
So
So it's kind of like where the greatest like need is. Okay.
you're going to start to see complexes that break Hund's rule, where we're not going to fill every d orbital with an electron before we start pairing. Okay, so we will continue on from here next time.